Hello and welcome to Calculus tutorial. We are going to take a look at something called the trapezoidal rule, and it's another way that we can evaluate a definite integral. So far we can use rectangles, we can use geometric shapes. The fundamental theorem of calculus is an amazing tool, but sometimes you can't take an indefinite integral to use the fundamental theorem of calculus. If your equation is too complicated, you often can't do that by hand. And so we need another way to find a definite integral. Rectangles are cumbersome, it takes too many of them too long. I think we can all agree on that. So there's a better way than rectangles. So instead of left or right rectangles or even midpoints, we're going to use trapezoids. And at first it doesn't sound much better, but if we start taking a look at these points, let's take the integral from -2 all the way to 3. Yes, I could fit rectangles on there, but it's not very efficient. Instead of making rectangles, I'm going to connect these points, and we're going to use these geometric shapes. That's way up here somewhere. And as you can see, yes, there is some parts that we're missing, but not very much. It's much better than rectangles. And I think I only have one good example of a trapezoid, and it's this one. So yes, technically sometimes these shapes aren't technically trapezoids, but the math still works out. This one here is a nice example of a trapezoid. So I'm going to draw that shape over here. How do we find the area of that shape? It's not a trapezoid like you're used to seeing, but it is a trapezoid. So the area of a trapezoid is base 1 plus base 2 divided by 2 times the height. So this is base 1 and this is base 2, and technically this down here is the height. Yes, we've got it turned on its side so it doesn't look like a height being vertical, but that is technically the height. And so this is the formula we're going to add up over and over again. So how are we going to translate that into our function? Well, base 1 is simply this y value, and base 2 is this y value. And so these are going to be our y values, and the height is this distance right here. That is the change in x, however wide your trapezoid is on your graph. And so if we want to take the integral from -2 to 3 of this function, what we're going to do is the first trapezoid, which yes, I know is a triangle, but treat it like a trapezoid. So the first base, this one over here, is the y value from f at -2, plus the second base is this height, which is f at -1, divided by 2, just like the formula says, times the height, which is 1, plus the next one. Well, what does the next one use? Well, it uses f at -1 plus the second height will be f at 0 divided by 2 times the height, plus the next one, the first height is f at 0 plus the second height is here, f at 1 divided by 2 times the height. So it's a little tedious here. You can see I'm writing a lot. So we want to take a look at how could I simplify this, because I'm not even done yet. I have to keep going. Well, what do all of these have in common? They all have a divided by 2 in common. So I'm going to factor that out. What else do they have in common? Well, they have the 1. They all have a 1. So yes, I don't have to factor that out, but I'm going to factor that out to the front. That is our height, and your height isn't always 1. Now, that will be multiplying by all of what's left over. So f at negative 2 plus f at negative 1. And here's where I'm hoping we can see the pattern. Plus f at negative 1 plus, now do you see how there's 2 f at zeros? Then there will be 2 f at 1s. Then there would be 2 f at 2s, because the 2 is used for this trapezoid and for this trapezoid. And then finally for f at 3, there'd only be 1 f at 3 because that is the end. And we could keep going there. It's a bit long of an integral. I should have done a shorter one. But that would give us a trapezoidal sum for this definite integral. And you can see it's much more accurate than any of our rectangles would have been. So, what is the actual formula? If you take the integral from a to b of some function, it is equal to, so the 1 was our height. It's not always going to be 1. It's however wide your trapezoid is, divided by 2. That is always a divided by 2 because that came from our formula, times, now you have f at your first x, so I'm going to put x sub 1, plus, now there are 2 of your second x's, so 2 f of the second x, and then there are 2 of the third x, etc., etc. So I'm just going to put dot, dot, dot. You do that as long as you need to, but then at the end, there is only 1 of the last x. And so I'm going to put x sub n. However many x's you happen to have, there's only 1 of the last one. So that is your trapezoidal rule there. And most of this you can just then plug into the calculator or add up by hand depending on how many x's you have. All right, let's do a quick example of that with the formula, and then we're going to do a word problem with it as well. All right. So let's use the formula and see how that works on an actual problem. Don't worry, I started with a much shorter one. So we're going to evaluate this integral from negative 2 to 2 using the trapezoidal rule and 4 equal subintervals. All right, so we're going to have 4 trapezoids this time. Not too bad. So the integral from negative 2 to 2 of 4 minus x squared is equal to, all right, so what is the height? Well, if we're going from negative 2 to 2, that's a distance of 4. And if we're doing 4 subintervals, that each one will have a height of 1. So I'm making it nice and easy there for us. So 1/2 times f at negative 2 is our starting x. That's where we're starting. Plus, then we move over 1 subinterval. That will put us at f at negative 1. But there are 2 of those. Then we move over 1 more. 2f at 0 plus 2f at 1. And then our last one is f at 2. So that will be just one singular f at 2. I'm guessing we can do most of this in our head. It's a nice easy equation. So f at negative 2, if you plug in negative 2, you get positive 4. 4 minus 4 is 0. Plus f at -1. So if I plug in -1, we get 1. 4 minus 1 is 3, times 2 is 6. If we plug in 0, we get 4, times 2 is 8. Plus, if we plug in 1, we again get 4 minus 1, which is 3, times 2 is 6. Plus, and our last one, if we plug in 2, we again get 0. So 1/2 times 12 and 18 is 20. 12 and 8, sorry. And then that is equal to 10. Now I guess one thing, this is an approximation, so let me make that equal sign squiggly there a little bit. So that's how you can use the actual formula for that. Remember, this is your height up here. It is not always 1. And whatever that height is determines on what numbers go in here and how those step up. Sometimes drawing a graph can also clarify that. A little tedious, but your answer is always going to be much more accurate than rectangles. You need a lot fewer trapezoids than rectangles to get some good accuracy. But where you use this most is when you just have a data-based question. So you don't have a formula, you just have a table. So coffee is dripping out of a coffee maker at a rate modeled by R at t. So this is our rate, where R is continuous and differentiable. R is measured in ounces per minute, and t is measured in minutes. Use a trapezoidal sum to determine how much coffee dripped out of the pot over the 5 minutes. So first thing I would say, like usual, whenever you get a word problem like this, always identify which of the 3 graphs you are given and what you are trying to find. So let's see, we are given R, which is measured in ounces per minute. That gives us a clue, and it's a rate. So R at t is a rate. It is a derivative. And if we want to know how much, that is an amount. That is this one. An amount. I'll use A for amount. So if we want to go from here to here, we need to take an integral, a definite integral. So we are essentially doing the definite integral from, it looks like 0 to 5 of R at t dt. We don't have an equation, so we can't use the fundamental theorem of calculus, and they are asking us to do a trapezoidal sum. So these are our x's and these are our y's. So if I do a trapezoid from there to there, there to there, there to there, there to there, and there to there, I'll have 1, 2, 3, 4, 5 trapezoids. What is the height? Well, that change in distance is 1 over 2 times, so it's the first x or the first y value once, plus 2 of these, plus 2 of these, plus 2 of these, plus 2 of these. Remember, only one of the last one. So that works out quite nicely because they were all equal subintervals apart from each other. If they weren't equal subintervals, then we would have to use the base 1 plus base 2 over 2 times height. Because the heights might not all be equal, you can't factor them out here. But we got lucky, they were all equal, so we can add these up and divide them by 2. So 10 and 30 is 40, 60, 74, and 76. Divided by 2 is 38, it looks like. So 38 what? How much coffee dripped out? We are measuring in ounces, so 38 ounces dripped out is what our approximation is. Alright, so there we have an example of how you can use the trapezoidal rule on a table of values when you don't have an equation. And trapezoids are much more accurate than rectangles. You have to do a lot fewer of them to have much better accuracy. But that's just one more way that we can find a definite integral.